let's see. So I will give you the calendar at some point or two. We're going to do the atom today, and then we'll move on to nuclear next week. That's going to go garbage. Bad for him. Okay. All right. So let's talk about the atom. What do you know? It's small. Yeah.
Nucleus.
We now know that the nucleus that has protons and neutrons. These guys are called nucleons. Okay. Protons and neutrons. It has electrons. The electrons in the nucleus, right? They orbit. There are quotes around that. Orbit around the nucleus. It's not quite an orbit like you think of with, planets going around the sun, but that's how I imagine. Okay. Thinking about it in terms of the historical path that the atom has, tread over the years. Back in the day, let's talk about, I don't know, maybe Newton's time, 1700s. They thought they knew what matter was made of. They said, hey, it's made up of these atoms. These atoms are little tiny indestructible spheres. Okay? That's their understanding of it. And to us now, that sounds really ridiculous, right? Like, of course they're not tiny indestructible spheres. But I want you to think back to when we were doing thermo last year. And when we were doing that modeling to talk about the kinetic energy of the atoms in the box, right? And we were like finding the whatever. For all of that stuff, we used the model of an atom as a tiny indestructible sphere. And that's as far as we needed to go. And that model of the atom works for kinetics, okay, for thermodynamics and the kinetic theory of gases. So the reason that I wanted to point that out is because even though we know it's not really true now, we still use it because it is helpful in some cases. When you're talking about thermo, it doesn't matter that there are electrons. Right? So that's just to kind of keep 1900, I can't remember exactly when J.J. Thomson did this stuff. That was the first like really big breakthrough into atomic physics. Before that, again, we had just kind of thought that whatever. In 1900s, Thomson developed. Well, do you know what Thomson did? Let me ask you. He was not. That guy comes next. Yeah. Yeah, he didn't, okay, so he didn't invent them, right? Right, but he did discover them. He was the first person to identify there were these funny charges, these funny negative charges. So there is, the charge isn't uniformly distributed, I guess is a way to.
Did you do that with oil?
That was Millikan. Did you know that Millikan is from Iowa?
Oh no,
He's from Iowa.
you told us that he was a fake and that.
I did tell you that. I've learned more about him since then. What's that? I don't know. I don't remember. I've learned a lot more about Millikan. When I was at the conference 2 weeks ago, I went to a whole like 2 hour workshop about Millikan. He was not the best guy in the world. He was. I've developed more of an appreciation for him.
It's just because he's from Iowa.
No, not just because. I'm not gonna swing him. No. But I will say that he did a lot more stuff than I. That's kind of my. I did learn that in his entire biography twice. And that was that the way for hours to perform the deed being getting married. He had to be pulled away so that he could go. Like,
Yeah, I agree with that.
yeah. Or something. Anyway, my favorite counterintuitive. Anyway, back whew, the electron. Again, before that we thought that there was this one that after having this image of the electron came up with what model. Because I think it's kind of funny that in the U.S. we still call it the plum pudding model, even though how many of you have had plum pudding? I've never. Bread pudding is fabulous, but it's a little. So what's the concept behind plum pudding? The plum pudding model.
It's like this, just like circle, like electrons kind of floating around, or like at certain positions, just randomly distributed.
Yes. Well, yes, yeah, more or less. So I know that some of the eighth grade science teachers still call it the chocolate cookie model, okay, which is something that we all have a little bit more experience with, right? Okay, so it's basically that you've got this kind of of goo, and that goo is positive, and there are negative charges inside. Okay, so you've got a positive charge throughout. It's positive. An atom. I mean, we don't. But again, this is like one step at a time, right?
Was that before the neutron and proton were discovered?
Yes. Yes. Yeah. So there's positive throughout with negative charges suspended in it. Okay, and that idea existed for a decade or so, and then there was this guy named Rutherford, and he kind of broke things wide open. And this is where we really start to talk about developments in the atomic theory. So in 1911, okay, along with two of his graduate students, Geiger, who you might have heard of the Geiger family, yeah, and Marston. And I don't know. What's that?
That I think that one of the extra DNA people have a name starts with an alpha. That might be right.
Yeah. So Rutherford and his graduate students did this breakthrough work, right? What did they do?
Gold foil, sheet of gold, a really, really thin sheet of gold, blasted it. Yeah.
Right. Shot particles at it. Now we have to break this up a little bit. And okay, so let's. We have a really thin sheet of gold foil.
Oh, and then didn't they have it surrounded by like what was it? It was something that would make the whatever particles as they went through or they deflected back, like light up so they could tell.
Yeah, so it was photographic plates.
Photographic plates.
Yeah. So okay, so we have a thin sheet of gold foil, and we're gonna shoot stuff at it, but it's not just regular stuff. Because remember what it was? They were alpha particles. So we have a thin sheet of gold foil, and we're going to direct alpha particles that we now know are what? Helium nuclei. But let's be really quite honest here. We had no idea that they were nuclei at the time because we didn't know nuclei at the time. Right? We're still living in the plum pudding model world, right? So we don't know that they're nuclei, but we have these charged particles, but they're kind of heavy because a helium nucleus has what? 2 protons, 2 neutrons. It's got a bunch of stuff. It's pretty heavy. I mean, all in all. And alpha particles are the result of some radioactive decay. That's where they got them. They weren't like, oh, let me take this plum pudding hydrogen at or helium. Like that's not what happens. But that's where the alpha particles came from. So the idea is, okay, that if with the plum pudding model, that alpha particle should shoot straight through. Okay, it will be deflected a little bit. It's going to go straight through because there's no reason for it not to be. Okay, And I also want to make very clear, and I have not done the research to find out, you have to remember, especially when we start talking about modern physics, that it wasn't that Geiger and Marsden were out to make this discovery, right? They were doing some sort of research about some sort of thing and thought this would be a good idea, okay? And they got a weird result. The weird result is what leads us to all of this new atomic theory, right? But they weren't like out to find this. And that's something that I really have to remind myself of that and to remind you all of that these things happen, not like it's not like they walk into the lab, we're going to find something new today, right? Like that doesn't happen. But they're making good measurements such that when they shot those alpha particles at the gold foil, instead of them going straight through, so as Luis was kind of suggesting, this gold foil is surrounded by photographic plates, and the photographic plates will light up, they will record when a particle has hit them, okay? So the alpha particles are coming through, they're coming in this way, like this, and we should expect a little bit of deflection, so some bright spots around in there. Now, most of the alpha particles did go through. But here's the weird thing. A significant number, so not like 2, but like, a okay percentage bounced back. So they came back this way and they hit back behind where they had come from. And that doesn't make any sense if you use the planetary model. Rutherford, in his way of telling this to the media, said, it was quite the most incredible event that has ever happened in my life. It was almost as if you fired a 15-inch shell, right, like big, at a piece of tissue paper, and it came back and like that's a little bit whoa, whatever. But in some ways, that kind of makes sense. Right? That doesn't make it. Why would it shouldn't do that? So that's weird. So that's kind of where we're going. We're trying to now answer that question. That's where a lot of this is, especially physics. So you make an observation, and you have to figure out what. Oh, we got to do this 17 more times. So Geiger and Marsden go do that. Okay. Do it 700 more times. Let's see if we get the same results. Oh, we do? Okay, now let's figure out what's going on, right? Okay. This experiment to try and explain the fact that some of the alpha particles went through. So we'll say some alpha particles went through, but some were deflected. Back. Okay. What does this imply? What does this tell us? There had to be something to do that, right? It's not just this little, this thin sheet of all this positive charge. That doesn't make any sense. No, there had to be something that actually, like, physically, right? Okay, what was it? Yeah, there has to be something in there where we've got a concentration of that positive charge. So instead of like goo or the uniform space positive charge, there have to be these concentrated places where we have this charge. So this leads us to what kind of model? Not the plum pudding anymore. The orbital or the planetary model? So the idea for the atomic structure, okay, is that there's a positive charge concentrated in the center, and then you have negative charges orbiting around. Okay. Now, is that the model of the atom that we work with today as chemists and physicists? It's close, right? The idea that we've got this nucleus and we've got these electrons orbiting, sure, right? Now, we know that the electrons don't orbit in nice circles, right? They live in these orbitals, and they're actually, they exist and don't exist. They're in kind of superpositions of states, and there are probabilities that they're in any of those places, right? That stuff is all, what do I want to say? That is all kind of built up from further explorations from this. But this is kind of the basic model that we still use. This is the model that is still generally taught until you get into how those orbitals are actually put together and how they kind of exist. If we really know how they exist, not a lot. And it's kind of it's where it's a lot of where chemistry and physics fits together, right? So the physicists like to model it, but the chemists like to use it, right? Like they're going to exploit it to do things. And I don't mean that in a bad way. Okay, I mean that in an honest way. Right? Okay. What's that? Yes, they do. I don't know that I would go that far, Luis, but if you want to live with that, sure. Okay, new story. Nope, not yet. We're kind of changing topics. Changing topics. What's that?
He said he was born.
Terrible, terrible. What's what? I try. Atomic spectra. We've talked about this. We talked about this when we were doing Astro, but I just want to remind us and put some things down to make us a little more full, I guess. So, we've only talked about this about 7 of course. But all matter emits radiation. Have you heard that before? I know, right? What is that about? Whoa! It emits radiation throughout the continuous spectrum, and we've seen those curves. Yes. Okay. We also know, I know, hint, right? I have no idea. That's so much fair. Rarefied gases. Okay, so when you have two, when you have gas that we put a okay. So when we have gas that's excited by a high voltage, okay, we also have radiation. But unlike the radiation emitted at the continuous spectrum, this radiation that comes from the gases that are amped up at high voltage, is that a continuous? No, there's the lines. You remember we said the lines that were the same as the absorption lines and that sort of thing. It's the same, but it's discrete wavelengths, okay? And the discrete wavelengths are distinct, or I'm trying. What's that? Oh yeah, it's oh, you're right. People in Chinese, and they're like the same except backwards. Sorry. What's that? No, it's like one of those like in the back of my brain things like discrete people. Discrete too, right? Sorry. And they offer a distinct signature for an element. Okay, that's known as the emission spectrum. So let's talk about this. We kind of just said that was true when we were doing Astro, and we just kind of left it there, and you're like, okay, sounds good. Let's talk about it a little bit more now. So we could and we could, instead of just using the cool glasses that are indeed quite cool, you can use a spectrometer, and so you can actually measure those wavelengths, like actually put numbers to it, right? Quantify things. So we're not quantifying. Okay, we're going to quantify those wavelengths, and then we're going to see if we can find out. 1889. Okay, there was a guy named Balmer, J.J. Balmer. Oh, do you not like Balmer? Do you know something about Balmer? I don't know. I want to know if there's scandal. He was studying the simplest of the gases. Which one would that be? Hydrogen. So, let me tell you a little bit about. I just think this is kind of interesting. Sorry. We'll just look at the hydrogen spectrum in the visible wavelength. Okay. So it's kind of interesting when you start talking about theoretical physics and start talking about modeling things. Okay. Modeling at the atomic and nuclear level is very, very difficult. Okay. There's a lot of quantum mechanics that comes in there, and we'll get to that, and all of that is really lovely and interesting. The entire, I took, well, I guess it was a full semester of quantum mechanics, and we were talking about how things work. How many elements did we talk about? One. Okay. We only talked about hydrogen, and we only scratched the surface. We didn't get into this will be a fundamental difference between our chemists and our physicists, right? So, hi, I don't know why you're talking to me. You turn that off. The chemists are like, they get on this really fast, right? Some physicists do, but talking about those quantum mechanical people and like actually looking at how to model and understand this stuff, really, even the best physicists in the world are still looking at hydrogen and really trying to understand how hydrogen works, which in some ways seems kind of silly, right? Like, it's simple. It's a proton and an electron. Like, how cool is that? But there's a lot more to it. So I want you to know that because there's so much in there. I just think it's kind of interesting. So anyway, Balmer looked at the hydrogen spectrum, and he saw the same four lines that you saw. I wrote that down, right? Just making sure. So 656 nanometers. He saw 486 nanometers, 434 nanometers, and 410. Said, that's interesting. There's got to be some sort of pattern. I'm an experimental physicist, so I'm just going to try and fit that to a pattern. And I'm going to play with the numbers and see if I can get them to fit in. And here's the function that they fit. 1 over lambda is equal to some constant. We're going to call it the Rydberg constant because times the quantity of 1 over 2 squared Jackson's minus 1 over n. Awesome ability to square things, just for now, okay? Where n is equal to 3 or 4, No. What's that? These are not lies, these are truths, right? You have an experimental physicist, somebody who's taking data and trying to fit the model for the data, right? Anybody else like that that's doing that for extended essay? What's that?
How far can it go?
Well, we know that there are 4 that we can see.
Right.
So for Balmer's purposes, he gets a 4, 5, okay? But as someone who's closed off in his mind, like, well, maybe this is just going to be, just go with it. That's what it's going to be. And constant has a value of 1.0974 times 10 to the 7th. You can go ahead and tell me what the units are. It's just a number. What's that? Does that make sense to people? Yeah. Cool. All right. So good for him. Now, again, this is pre Gold Foil, right? This is even before Thompson had done his stuff. Okay? So this is here. I see these lines. Oh my gosh, I'm just fitting stuff. That's all we can do. No one even lines yet. A little while later, and I don't have the dates for these, I apologize. But there were two other, there's one named Lyman, who did a similar sort of deal. He looked at hydrogen, but instead of looking at it in the visible part of the spectrum, looked at it at short wavelengths. So in UV part of the spectrum. And he found that the emission lines that he was measuring a function, and the function was 1 over lambda is equal to r times the quantity of 1 over 1 squared lambda. I can do that one. That's got to be one. I'm just, I know, good for you. You can do your squares too. I'm proud of you. Minus 1 over n squared, where n is equal to 2 or 3, dot, 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 dot. And then there was another person who was looking not at the short wavelengths and not at the large wavelengths. That would be infrared. Yeah. And his name was Paskin. Long wavelengths, so in the infrared part of the spectrum. And he found that the wavelengths that he saw followed this pattern. Good job. Which is what? I'm not going to judge the fact that he's like, so, as an experimental physicist, well, that's pretty cool, right? There's some sort of pattern. I like it. Good for us. So now we've found observations, but there's one big question there, and that is, why? Like, well, I do, but at the time I didn't. This nice formula, that's cool, but what are we going to do? So, going back to our story. There's Rutherford, 1911, shot those alpha particles with the gold foil. They were like, tell me what's going on. They had heard about this work that Balmer had done and all of that, but they're, I mean, whatever, like, who cares? In 1912, new colors. There we go. What's wrong? Sure. I don't have any idea. Yes? There you go. Okay. He's sad about the. All right. Back to physics. In 1912, there was Rutherford, right? He was probably trying to figure out what. And he brought in a new grad student. So I don't know if you guys know how graduate school works, but how you get your undergrad and you're looking for the lab tour. So if you're one of the top people in graduate, the best physicists so that you can work under them. Doctoral, what I was trying to say, advisor, then, you know, good things can happen. Kind of And so Rutherford, being all awesome, gets the best people, right? The best people. And one of the people that came to work for. Okay. So Niels Bohr, so he's a graduate student at the time, kind of just trying to get this stuff under his belt. He had some sort of feeling that the planetary model was okay, like we were on the right track. He was kind of convinced that the planetary model made sense. It had validity. But he didn't think it was going to be as simple as just saying, yes, that's all well and good. Okay? There was another thing that was happening in physics at the time, besides all this atomic stuff. What else was kind of going on? Do you guys know your physics history? What else was going on at this time? So Einstein published his papers in 1905, right? So we're kind of talking Einstein, and we're talking the birth of quantum mechanics. Okay, so we're going to talk about quantum mechanics later. This book kind of does things in a backwards order from the way that I teach them in other classes, but I like it this way. It'll work. So short version of quantum mechanics, short version, 15 seconds or less. Okay, something like that. Okay, instead of having everything in continuous measurements, quantum means quantized means discrete amounts. Okay, that is the basis of quantum mechanics. There's a lot to it. That's not it, but that quantum mechanics basically values are constants. We have these things, so things have a certain much, but so quantum mechanics is kind of coming into its own right now as well, as is atomic physics. Like it's kind of all mixing together. And Bohr in order to get to incorporate quantum mechanics into his okay. So in 1913, a year later, he published his idea. Okay, we are going to spend much of the what's that? Okay, you sure? Okay. We're going to spend much of the rest of the class kind of going through, thinking through his idea. Okay. There are 4 assumptions that Bohr had to make in order for his idea to work. So again, just kind of thinking about this in terms of the historical context. Just like Rutherford didn't walk into the lab and say, I'm going to make a new discovery today, right? As a theoretical physicist, he's not going to say, I get it all, here it is, this is what's going on, right? Okay, he's got to start somewhere. And from that place, he's got to take steps forward. And he's like, okay, well, this doesn't make sense, but if I make these why? But if I make these 4 assumptions, then it's going to work out really nice. So let's go with it. Because maybe at least okay. So he published in 1913 this theory that has 4 assumptions. And you actually do need to know these assumptions. I've seen IB questions that say, like, something, something, something. What was another assumption? So these would be good things to know, is what I'm saying. I've seen these questions. Assumption number 1 is that the electron moves in a circular orbit around the nucleus. Again, we're just trying to get somewhere. He didn't say it was all perfect, but if I make these 4 assumptions, we're going to make progress. It does, and that's where we got to start. I'm not going to start with like I don't. uranium, that might be a little bit more challenging, okay? If it moves in a circular orbit, we know this from our conversations last year, that there has to be something that's causing that force, right? Or that is imparting that force to cause the circular motion. What's that? Oh, yeah, because we got electric charge. That negative charge, we know that exists, as Thompson told us, and we now have this theory that there's a positive charge in the middle, and we know positive and a negative, what do they do to each other? They're going to attract, right? Okay, so that would be an attractive force. We've got some change of velocity that goes around the Earth, electrons go around the nucleus. Okay, so we're going to say that the electric force, the Coulomb force, that's K122 over R squared. And nice. I love this whole derivation here because it's like awesome review of all of it. Okay, the electric force is providing that. That was assumption number one. Assumption number two is that there are only certain orbits that are stable. Okay. This is weird. This doesn't make sense. This is where quantum mechanics is starting to come in. Okay. Only certain orbits are stable. And let me tell you why we have to make that assumption. If you have, well, this is kind of backwards. If you have an electron that's going in a circle, is it accelerating? Yes, because it's definitely changing direction. If you have a charged particle that's changing direction, it should be doing what? What is a charged particle that's accelerating? What's that going to give off? EM, what is radiation, right? And if it gives off radiation, that means that it should be losing energy. And if it's losing energy, then really it should be spiraling in, which would mean that there are no atoms, which would mean we don't exist, if this is the theory. You see what I'm saying? So that was a fundamental problem that Rutherford and all the rest of us were struggling with. Right? If you've got this electron that's orbiting, it should be giving off electromagnetic radiation, and if it's giving off that radiation, it should be spiraling in, it shouldn't be. Right? That's a fundamental issue. Okay, friends, I'm working with it. I don't understand why, but if we say that certain orbits are stable, and at these orbits, okay, the electron doesn't emit radiation, and so only classical mechanics explains the motion. Then we've got something. We've got a step, right? So again, a step in the right direction. Is it the end all be all? No. But is it making progress? Yes. That's number two. Number three. Assumption number three. There is a time when radiation is emitted. It's not while the electron is going around. But the electron emits radiation when the electron moves from one energy state to another. Okay? So radiation is emitted when the electron, I don't know that, but this is how I've seen it, jumps from one state to another. And this is independent of orbital motion. Yeah. Is that radiation
only when it goes from high to lower?
Yes. Yes. And it has to absorb. Now, let me back up and say the answer that I answered yes to answer not as
Okay.
all but really
And just go back to the second one. From our perspective, it wouldn't make sense for it to be that radiation that's going to a higher energy doesn't higher me farther away from
right, it has to absorb energy to get. Mhm.
so
Exactly. You're giving it energy. Yeah. Exactly. Physics.
what we learned.
You did learn. I'm just teaching. Last one. The size of the orbit is I can't spell. That the angular momentum, I'm going to pause there for a minute. Talk about what angular momentum is, because we haven't talked about it. What's that? I don't think we've talked about angular momentum, have we? I get to teach about angular momentum, like, I don't get to teach but I get to teach about angular momentum, like, all the
It's
time.
cool because like I asked about it last year. It pops up everywhere.
Mhm. I know, right? It is. You know what linear momentum is, right? Yeah. Linear momentum is smash each other, linear momentum is conserved. Angular momentum is conserved off. So angular momentum is it's all about this would be like single figure skating. Okay? You have it's usually the end of the routine. Right? The skater has their arms out and they're spinning and they turn the hand and they spin faster, right? That's because of angular momentum. So linear momentum is angular momentum has to do with the angular velocity and it has to do with the radius and the radius of the ball, which is why things like neutron stars spin really, really fast, whereas big stars spin very fast. Angular momentum has to be the smaller it is, the faster it's going to be, or little. What's that?
Yeah, the same math.
Right, but it's concentrated. Yes, exactly. Okay, so angular momentum has to be conserved. Everybody agrees with it. Okay, that's not Bohr's not going to say. But not only is it conserved, Bohr says like make it has to also be. Why? I don't know. But I know that if we apply this constraint, then it does then things happen. So angular momentum, so linear momentum is mv. Angular momentum is mvr. And Bohr says that in order for all of my idea to work, this has to be constrained such that the angular momentum is n, some number, times h over 2 pi. H is Planck's constant. Okay. Often, quantum physicists get lazy with this h over 2 pi term exists a lot. Okay. So instead of writing h over 2 pi, h over 2 pi, they say so that's going to be n, the same n, times h with a line through it. That's called h bar. And they just call it h bar. So if you ever see that, and I don't know that your book uses that a lot, but if you ever see it, h bar just means h over 2 pi.
Was it someone else trying to write H over 2?
Right? We'll just leave it. It's fine. You know what I mean, right? Okay, so life is good? 4 assumptions. You want me to do some more magic? Yeah, where's the enthusiasm there?
Yeah.
That's right, Lander. That's what I wanted to hear. All right. We're going to be smart with four. Here we go. We're going to use some assumptions. We're going to use all the physics that we knew. Sound good? We're making the assumption that we've got an electron that's going around the nucleus, orbiting in a circle, yeah? Okay. If we do that, if we make that assumption, then we're just going to write down what we know, okay? We can talk about the potential energy. I don't know